Okay, so let's consider air columns, in addition to strings, as a fundamental source of sound that is all around us, and especially if you're a musician, you're quite familiar with some of the practical manifestations of this phenomena, even though you may not realize it yet so much. But we may produce standing waves in the columns, or the tubes, or the pipes, the cylinders, like a pipe organ, wonderful example. You got all those pipes. We're setting up standing waves in those pipes. And that produces a lot of sound coming out of those pipes. Well, the pitch, again, is related to the frequency. It's determined by the lowest resonant frequency, the fundamental. However, it may not always just be the fundamental that's set up in the particular tube. But what's moving here? So for the string, the medium was the string. But now, the medium is the air. It's the air inside the tube that's actually moving, displacing the air, rather than the string. So that seems quite a bit different. Actually, with the string, you're vibrating the air, but then you're moving the air, for that matter, too. I mean, you're vibrating the string, but it's pushing on the air. But now it's the air itself that we're thinking of as having the standing wave. So the standing wave inside the tube, we can think of as a displacement wave or a pressure wave. All right, so we started out our study of sound by looking at the distinction between those, so review that if you want. We could consider a sound wave, which is a longitudinal wave, as a sinusoidal wave, like we did in the introduction, as either being displacement or pressure. But when we just discussed strings, we considered it a displacement wave. In fact, we're just basically looking at what the string is doing. The string is the medium, and it's actually displacing the string. So we're going to do the same with the displacement of the air molecules and represent those as in a sinusoidal manner as well. So let's get on with it. So we have open tubes. An open tube is simply open at both ends. The fundamental, or the first harmonic, there it is. So we got this tube of length L, and it's open here, and it's open there. And what we're setting up in here is the lowest fundamental resonance. And it's interesting because the air actually has a tendency to want to set up longitudinal vibrations consistent with this. And here is a node. This is going to be a node. It's a place where the air is not moving. And then we have antinode over here, a place where the air is moving the most. So we have to have a node and an antinode for a standing wave. That's the minimum. This is the antinode. Okay, so what's the length of this tube? The length of the tube with respect to wavelengths. Well, it's a half a wavelength, just like before. Think about it. Here we are. We start here. This is a quarter wavelength. This is half. This is really stretched up, but we would have to go way up. Oop, getting away here. Way up here for way up to here for 3/4, and then up like that for a full wave, where we repeat this again. All right. The frequency, velocity over wavelength, as before when we looked at, well, all the time, this is true. Wavelength is 2L again, so it's just what we had for the string. What's the difference? We have antinodes at the end instead of nodes. We have a node in the middle instead of an antinode, as with the string. Isn't that cool? All right, so the next resonance is going to have two nodes, one there and one there. And we have antinodes at the end still. So the second harmonic has a frequency compared to the first of just double, just like before as well. We've got the vibrations happening twice as quickly. And how much length, granted it's the same length as before, but how many waves are in here? Well, it's one wavelength. We've basically taken this thing and squashed it down to half the width and then doubled up on it. So we got a full wavelength in there. And then the next one, we have 3 nodes. There they are. 3 nodes and 2 antinodes again. So the third harmonic has a frequency of triple the original. The length now, what's the length? Let's see, 1/2, nope, 1/4, 1/2, 1, this is 1 and a half. So the connection, the analogy to the string is very tight here. Just the nature of the standing wave with the being a displacement wave here looks a little different. But once again, for each harmonic, each subsequent harmonic, we increase the length of the column by 1/2 a wavelength. Now that's a little misleading. Of course, the column is the same length, but when we refer to it in terms of wavelength, it's a longer column. In other words, the column length is equal to more wavelengths. But of course, the wavelengths themselves have shortened so that the total amount of length is really the same. The wavelength is just shorter. Okay, and now we're going to consider closed tubes in addition to the open tube analysis here. So closed tubes are just exactly what they sound like. They are tubes that are closed, but closed only at one end. If they were closed at both ends, you wouldn't hear nothing, because the sound you hear comes from this antinode here, moving the air a lot, producing a longitudinal wave that emanates out from that antinode and making a sound wave through the air, as always. So look at this first harmonic, or the fundamental, in the closed tube. This is not much of a wavelength. This thing is really stretched out. The requirement is that it's always a displacement node at the closed end. There's a real simple reason why. And it's just this. Can the air move down here at the closed end? No. There's a barricade here. This is inside a cylinder, a tube, and it's blocked so the air can't move. Okay. Now, what's the length? How much of a wavelength is this length? You're starting from, you could say, the equilibrium position to the maximum. That's it. Let's see, if it was 1/2 a wavelength, it would have to go up there and back, back down again. So this is only a 1/4 wavelength. 1/4 wavelength. So there's a fundamental difference between the closed tube and the open tube and strings. Open tube and strings, you start with the fundamental being 1/2 a wavelength. The closed tube, you start with it being a 1/4 wavelength. Frequency is velocity over wavelength, and if we solve for this, you multiply this by 4, you get V over 4L. So that's the frequency of an open tube fundamental vibration. And it's 1/2 of the open tube, isn't it? 1/2. Not the same as the frequency of the open tube fundamental. Open tube fundamental has a higher frequency because you're setting up 1/2 a wavelength, not a 1/4 wavelength in the tube. All right, so how about the next harmonic? The thing is, the next harmonic, the requirement is to have a node at the closed end. So here it is. And you have to have an antinode at the open end. Well, the next antinode is going to look kind of like this. My drawing isn't perfect, but, well, how much of a wavelength is that? It's a lot more than the previous one. There's 2 nodes. How many times the frequency? 3 times. There's 3 times the wavelength jammed in there. So instead of 1/4 of a wavelength, it's, 1/4, 1/2, 3/4. 3/4 of a wavelength. Frequency is velocity over speed over wavelength, which is, okay, if you solve, you get that. When you solve for lambda 3, you got 4/3 L. So you put that in the denominator and you get 3/4 V over L. So it's 3 times the frequency of the fundamental. And then, next one, the 5th harmonic. Notice the harmonics are based on the fundamental. So here's the fundamental, and this is 3 times more. The fifth harmonic is the fifth. There's 3 nodes, and there's 5 times the frequency. It's 5 times the frequency of the fundamental. What's the length? You got 5/4 of a wavelength. 1/4, 2/4, 3/4, 4/4, 5/4. It's all in there. Okay. Frequency, speed over wavelength, 5/4 V over L. 5 times the frequency. Now, note for each subsequent harmonic from here to here to here, how much does the column length change in terms of wavelength? Yep, same thing. Half a wavelength for every single one of these situations. Strings, open tubes, closed tubes. However, there is a fundamental difference between the open and closed tubes. How many harmonics can the open tubes have? They have the original. Can they have the second? Yes. Third? Yes. Fourth? Yes. Any harmonic. Closed tubes, because the fundamental is only a quarter wavelength, when you add a half a wavelength, you're tripling it. And that same, because it's based on the fundamental, you can only have the odd harmonics, third, fifth, seventh, etc. And that is a good intro to the physics of the resonating tubes, open tubes and closed tubes. And next we will consider beats in our next lesson.